our first speaker this morning is Eva Pfaff, and she will talk about train track automata for outer automorphism of free groups and geodesics in outer space.
Okay, so thank you for the introduction and the invitation and for coming at 9 a.m. in the morning. And also to Bob Moses for my being here. So the talk's a little bit of an unusual talk because what I want to talk about is, in some sense, some bigger question that's been brewing in the back of my mind for a while that I still don't know how to answer, but these different pieces that have been giving me possibly hints of what's going on. If you want to tell me how to answer it, I'm also very welcome to that. So, like most of my stories, so train track automata for outer automorphisms of free groups and geodesics in outer space is a tale of two interconnected themes. So I have asymptotic, dynamical, out-FR, conjugacy, class invariants, so both these things I'll tell you about as we go along. And one can think of, right, if you have a matrix and you apply it again and again and again, then inputs are converging on eigenvectors, and then the eigenvectors tell you again about what the matrix is like. And that's kind of the notion of an asymptotic, dynamical, conjugacy, class invariant is something like that, which tells you limiting behavior, but then that actually tells you about the original object. And then geodesics in the parameter space of weighted graphs. So Culler-Vogtmann Outer space. So I'll tell you more about these things as we go along. Sometimes there's a lot of definitions in outer automorphisms of free groups. Anytime you give a talk, it's sort of like, where are we going? And so I've kind of outlined this so you can kind of keep track. There is a reason I'm telling you about what I'm telling you about so that we can go somewhere. And so I will kind of repeatedly show you this to kind of see where we're going. And this is a fuzzy described way of understanding this bigger question of geodesics in outer space. So the group that I primarily study is the outer automorphism group, the free group. So we start with a free group, I guess I can even point here, of rank R, and then X1 up through XR is a free basis. So all the elements are strings of those and their inverses. I really look at the outer automorphism group because we have to quotient by automorphisms for base point reasons. If you want to, usually it doesn't really hurt you to think of the automorphism or self-isomorphism group of the free group. If you want to be technical, so that you do quotient by the inner automorphisms, you have one inner automorphism for each element of the free group, like A here. What does it do? It just conjugates everything by it. So this is the group that's behind what we're doing. I immediately move to a more topological way of looking at things. And here's kind of a basic example of a topological way of looking at these, so representative of an outer automorphism. So anytime we talk about an outer automorphism or automorphism, we just need to talk about where the basis, the free basis elements go. So here I have an automorphism that's the basis element X1 goes to X1, X2 inverse. The basis element X2 goes to X2 inverse. The basis element X3 goes to X3, X2. And then what is one way to get that as the induced map of fundamental groups? So one way to get that as the induced map of fundamental groups is to identify, so we're going to identify the fundamental group with a free group. And the way we're doing that is by this loop's getting identified with the basis element X1. This loop's getting identified by the basis element X2. And this loop is getting identified with the basis element X3. And then to get the correct induced map of fundamental groups, I would just send X1 over the X1 loop and then the X2 loop backward. These are the same as there. X2 goes over the X2 inverse, so I send the X2 loop over X2 backwards. X3 goes over X3, X2. So the X3 loop goes over the X3 loop and then the X2 loop. So that would give you the correct induced map of fundamental groups. And as we'll see, we'll need to do something to tweak this because it's not going to capture the asymptotic behavior right off the bat. Okay, but because I told you that way of looking at them, for those of you who are more familiar with mapping class groups, so I think that graphs on their own are interesting. So I don't believe we have to justify ourselves by mapping class groups, but I know that it helps orient people as to what's going on. So in rank 2, we have this exact equivalent So you can think of your surface homeomorphism and then deformation retracting it onto the spine. And now we've got a homotopy equivalence of a graph. So its induced map of fundamental groups is an outer automorphism. Again, if you had the surface homeomorphism, now we can keep track of how many times does the A loop go over the A loop and B loop, how many times does the B loop go over the A loop and the B loop. So you can have this in the back of your mind. And in fact, I'll give you a little bit more of a picture to have in the back of your mind by showing you some kind of how the asymptotic dynamical conjugacy class invariants work a little bit in these settings. So the vector 1, 0 would correspond to the A loop. This happens to correspond to a particular pseudo-Anosov homomorphism, if you know what that is. Otherwise, just think generic or dynamically minimal. And so if I apply this matrix to here, I get this vector, but that's also saying that's corresponding to, if I take the A loop and I apply the pseudo-Anosov that corresponds to this, I'm going to go twice in the A direction and once in the B direction, so twice and once. I would keep on doing that, and then as I got over here, what would happen, so I've approximated my lamination with a train track, but here I'm converging onto a train track. Over here, these vectors are converging onto an eigenvector and an eigenvalue. And then, so I'll talk a little bit about some invariants, and here's what they are in this picture. So the the eigenvector is corresponding to the lamination, which is approximated by this train track here. So people talk about indices of, so if you have a pseudo-Anosov and you have the invariant foliation, it has an index list. And this, we have some notion of an index or an ideal Whitehead graph in this setting also. This dominant eigenvalue here is going to correspond to the stretch factor or dilatation in these circumstances. And so those are just in these notions, we have the picture in your back of your head as we kind of go through what I'm doing in a probably less familiar setting. Okay. So now, as I promised, so in order to talk about these conjugacy class invariants and geodesics, I'm going to need to introduce train track maps. And the way that one can think about it is sometimes you need like a normal form of a matrix in order to see the asymptotic behavior immediately, like where you can see the eigenvectors and so on immediately. So remember that I talked about, we have these topological representatives where the induced map of fundamental groups is your outer automorphism. And then, but the reason we don't like this is it's not going to capture the asymptotic behavior immediately because, for example, let's look at what happens if I take this, I can point. Okay, if I take this X sub one loop and I apply this, well, this looks fine. I don't see any reason why this is a problem yet. But if I apply it a second time, what I'm going to notice is there's this kind of cancellation. So you can see that you're not having consistent behavior when you're growing and then you're collapsing back down and so on. So this is what Bestvina-Feighn-Handel result in a paper that they credit with being written here, by the way. So if we have a fully irreducible outer automorphism, you can think of that as just like the dynamically minimal generic elements of the outer automorphism group of the free group, or if you like definitions, it's that no positive power fixes the conjugacy class of a proper free factor. In that circumstance, also a little bit more generally, but we're always going to have these train track representatives. So this is really, the definition. You want the correct induced map of fundamental groups, and you want that it's locally injective on the interior of each edges, no matter how many times you apply it. But you also have that, so I'm not going to exactly explain how this algorithm works, but they have an algorithm, which is a quotient map. So it's much more complicated than in this. So schematic, I'm reminding you, this is a schematic cartoon picture, because if you stare at it too long, you'll realize that I'm lying. But basically the idea is there's this quotient map. Down here, you get the train track map, which has a correct induced map of fundamental groups, but it's locally injective on the interior of edges, no matter how many times you apply it. And you can kind of trace through and see that, if the X1 loop right? Over here it goes to the X1, X2 inverse loop. When I push it down here, I should get the same thing as I take the image of the X1 loop and then I go over. So you actually do kind of get this picture, but usually the quotient is really actually quite complicated, which is why I draw a schematic instead of showing you something which like things going all over the place. But the point is you get a different graph, same induced map of fundamental groups, but now it's going to immediately show the asymptotic behavior. Okay, so those are these train track maps, a little bit like a normal form of a matrix or something, where you're immediately going to see the asymptotic behavior. You have the induced map of fundamental groups being your automorphism, and they're locally injective on edge interiors. And then because these immediately show the asymptotic behavior, we can use them to figure out the conjugacy class invariants and the geodesics. Okay. So here's the idea. There's going to be some very mild lies. I'll actually kind of tell you where the lies are. But basically, just like in the other setting where I had all these surfaces in a row up there and the curves getting more and more complicated and so on, we're again going to iterate a loop, but now we're going to do it inside a graph. And if we do that infinitely, we're going to converge on the lamination leaves. So there is actually a fully irreducible behind this. So if I take, so you can kind of see, and I actually like making it like this because I'm a little enamored with the fact that the lamination leaves kind of have this nice nest. If you take a high enough power, this nice nesting inside, and then they get infinitely big. So they have this kind of beautiful like dynamics themselves. So here's your picture if you're a pseudo-Anosov person, that your ideal Whitehead graph are kind of going like this. But in our setting, what we're recording is how these lamination leaves are going to enter and exit the vertices. And so if some iterate, or if the lamination leaf passes over from here to here, then I'm going to put an edge there. There is, just so that these are asymptotically stable, there is a little bit of removing of edges, or sorry, removing of vertices or gluing of vertices. It's a little technical. If you want the actual definition, then you can ask me afterward. But basically what it's doing is it's recording how, as I apply my map again and again, the images of the edges are passing through the vertices, which you can kind of think of like the singularities.
Excuse me, may I ask you something? There was a question online of how is the construction different to Stirling folding?
How is the construction of what different from Stirling folding?
I didn't quite understand the question, so sorry. Maybe I'll ask.
Okay, I'll talk a little bit about Stilling's folds later.
The person wants to ask Bestvina-Feighn construction.
Oh, it's different. I know that it looks a little bit the same when you kind of don't know, but there's a different purpose. Like, so there's a whole bunch of moves in the Bestvina-Handel algorithm that are made to make it so that when you apply it, the interior, when you apply your map to edges, you don't have any of this backtracking. And so the algorithm is actually different than in Stilling's folds, but there's some overlap. And so sometimes, yeah, you have to look at the two carefully. They are kind of intricate. I'll talk a little bit about Stilling's folds. I won't talk about the algorithm because it's actually quite intricate and complicated. Yeah. Okay. But it's beautiful paper. I recommend it. Okay, so these are these invariants that kind of tell us the asymptotic behavior, like what happens at the vertices or singularities, how do you pass through them? And so now I'm going to talk about, so first I'll talk about outer space, so I can talk about geodesics in outer space. So you'll get more slides than just this. It happens to be true. So the outer automorphism group of the free group is the isometry group of the deformation or parameter space of metric graphs, or like weighted graphs. And so why don't I tell you what this is? I could say more there, but let's just actually tell you what it is. So here is, I kind of chose a definition that might be the happiest for Teichmuller space people. And then I'll kind of go through actually what it is. So a point in outer space is a marked metric a graph here, the valence of each vertex is at least 3. So I didn't write that here, but only think of graphs where the vertex of each valence is at least 3. There are other versions of outer space if you want leaves and stuff like that. Okay, now there's also the data of, I want to keep track of how the fundamental group is identified with the free group. And then I also want to keep track of, I want lengths on the edges that add up to 1. Okay, and that's like the version of a metric here. So let me explain a way to kind of understand it. And here's like in rank 2. So take each of your graphs that have the correct fundamental group. So I fixed my rank. I'm going to take each of the graphs that have the correct fundamental group and the valence of each vertex is at least 3. For each of these graphs, I'm allowed to put any lengths on the edges that sum up to 1, right? So the lengths of those edges give me, right, some coordinates. They have to add up to 1. So those are coordinates inside a simplex. So for each of these graphs, I have a simplex. And now I'm going to allow myself any identification of the fundamental group with the free group. And so now I have to have a simplex for each of those identifications of the fundamental group with the free group. There's multiple equivalent ways to think about that. I could also say I have a simplex for each basis, like free basis of the free group, or you could say I have a simplex, like I start with one where it's just the standard basis, and then I apply my automorphism to get all the others. Now, how do I move between? So now for each of these graphs where the valence of each vertex is at least 3 and I have the correct rank of my fundamental group, how do I move between them? Well, what happens is, right, because if a length goes down to 0, so imagine this length goes down to 0, now I'm on a face and I have a graph like this, but I might be able to get to that same March graph by making some length over here go down to 0. And so then those end up being glued along that face. Okay, so it ends up being a simplicial complex, but some faces missing. Why are there some faces missing? Well, let's, for example, look at this one. And if I squeeze that all the way down and made that length 0, now I have the wrong rank to my free group or my fundamental group. So that would actually be on the boundary. There's other stuff on the boundary. But some of them are actually like graphs of groups if you like those things. Okay, you good? I haven't been asking you for good. Okay, everybody's good? Questions? Okay. Okay, I'm not going to go deeply into the what the distance is on outer space, but there it is if you like that. I will tell you a few things about it. I'll tell you that it's asymmetric. So the distance
was gamma is the metric graph. What is gamma?
Yeah, so gamma is a metric graph. How do you get between them? You look for, yeah, the rest of it makes sense to you. Okay. Yeah, the rest you could probably guess if you know metrics and calculations. Okay, so the distance to get from here to here might not be the same as the distance to get from there to there. That's not like, there are lots of things that work like that. Like if you're trying to go drive in and out of a city during rush hour. But there's also, I guess the Lipschitz metric on Teichmuller space, I think, is also asymmetric. Yeah, okay. But why do we like it? Because we like geodesics, and there's a geodesic in the form of meaning that getting from here to here plus from here to here is the same distance as going from here to here. So along your geodesics. So there are geodesics, and they have this nice property that relates to Stallings-Fold decompositions. So as you go, and to the automorphisms and so on. And so you can ask different people why they like this, even though it's asymmetric and so on. My personal reason is because I think the geodesics are pretty. Speaking of which, geodesics. So I'm going to explain to you how to get geodesics coming from outer automorphisms. There are other geodesics. There are either also other fold line geodesics. I think there's way too many geodesics. I'll talk about that later. But I will show you what I'll show you at least how to get them from outer automorphisms or fully irreducibles. Okay, so to Stallings, as in the question. So Stallings decomposed. So we're gonna pretend, we're just gonna talk about this in like the nicest fully irreducible train track setting. So we're gonna take this outer automorphism, G, okay? And what Stallings does is this iterative but finite process where I'm going to take two partial edges that have the same image under this map G, and I'm going to gradually zipper them. So you can see I'm in the middle of zippering them here until they're fully identified. I get this map here, which then is going to factor through. So now I have another map here. So doing the fold, and then this gives me this. Now I can apply the same process. I zipper again, two partial edges that have the same image. There's a finite process. I end with a homeomorphism. So Stallings did this, I don't have the date on there, a while back. And Skora made this continuous. And so you could kind of think, so this has 3 edges. So I get a 2 simplex. This is 4 edges, so I get a 3 simplex, so like a tetrahedron. So I have like a triangle, tetrahedron, triangle, tetrahedron. And in fact, that triangle's on the face of the tetrahedron. And then again, another triangle. So you can imagine I'm going through the tetrahedron, hitting the face, the tetrahedra, hitting the faces as I go through. And so you can kind of see that as possibly a geodesic in outer space. I like this picture. So you can get mini geodesics. So here's one way you can. Another way is you can get multiple train track maps for fully irreducible. But you can have different fold decomposition. So the way to interpret this picture is to go from, my map is going from here to here. What does my map do? It sends the A loop over CBCA. It sends the B loop over CBC. It sends a C loop over AC. And then the different ways that I could fold come from the different identifications of partial edges with the same image, right? And so you can kind of see how you could get all these different kinds of folds. You could also do, you could decide to do 2 folds at the same time, which is how you can really end up with infinitely many different kinds of geodesics based on your choices of the folds. Now, so this is something I spent a lot of time, I've been working with Chichok Singh a certain amount. If you ever get an opportunity, you should talk with him. He's amazing. We spent a lot of time actually kind of playing with determining kind of, is there a best way to fold, with a little bit of inspiration in the back of our minds of kind of like the AGO splitting sequences. Anyway, he was an AGO student. Okay, so you can have multiple train track maps from a single fully irreducible, multiple ways of fold. So this, I'm tending to put on this side, if you're a Teichmuller space mapping class group picture person, this is your picture where you have you have north-south dynamics in a single Teichmuller axis running from the repeller to the attractor. We have almost the same picture because we do have north-south dynamics, so that should be, is it Levit and Lustig? I might be lying, it might be Cohen and Lustig. I think it's Levit and Lustig. You do have a repeller, you do have an attractor, you do have that these axes run from the repeller to the attractor, but you have lots of them. And they're all kind of encapsulated together in the Mosher-Handel axis bundle, Handel-Mosher axis bundle, which is something that we look at. Okay, so you get fully irreducible, you get these train track maps, which are these nice, these nice ways to look at them that encapsulate the asymptotic behavior and so on. We can decompose these by this procedure that identifies partial edges that go to the same place. Then you iterate that again and again, you get these axes that run from your repeller to your attractor in outer space. Okay, we good? Okay. So now I'm going to enter the part of the talk where I'm going to vaguely say a bunch of things about a bunch of results.
Conjugacy classes connected with closed geodesics, is that something?
Well, you mean like in the moduli spaces and quotient out by the outer automorphism group action. So it's a little bit more complicated than in the Teichmuller space setting. They will give you these closed geodesic loops down there, but there's a lot of other stuff that gives you these closed geodesic loops down there. That the only way to distinguish the ones coming from fully irreducibles is there's some kind of contracting property they have that the other ones don't have. But we have a lot more of a messy circumstance, but we kind of get to this, that this is one of the things that we are trying to keep track of, is counting these closed loops. Okay. So now you get to the part we're going to talk about a bunch of results in some sense, some of them, I will admit, I was interested independently in the random walk stuff because it really bothers me when I don't know it's typical. That's the kind of thing that eats at me until I figure out with other people how to solve it. But it does also kind of fit into this picture I've been trying for a while to kind of build in my head. Okay. So I won't like exactly state a lot of them, but these are kind of where I've been going to try to figure out what's going on. So way back originally, so Maher and Veach independently proved that the Teichmuller flow is ergodic and mixing and everything. And Eva told us, you know, oh, you don't know any of this about outer space. Why don't you first? So he said, Maher first proved that there was a geodesic dense in the quotient in the moduli space. Why don't you first see if you have that for out FN and the outer space? So this is from a long time back with Algom-Kfir. There's some mild lies where in like this reduced outer space, but we also, at the time, now I think we could actually make it a full geodesic. I think I see how to do that. But at the time we did a geodesic ray, but we did get this dense geodesic in this kind of meaningful quotient. And so we're like, okay, so there's hope that we're going to have something similar. It's quite a while back. So I think that this fits in. So this fits in my mind. I don't know if this is why other people cared about it. So Milan Bestvina asked us about if you, with respect to the hitting measure for like a reasonable random walk. So the boundary of outer space has R trees, so delta hyperbolic, geodesic, metric spaces. So it has R trees, and what do they typically look like? So in the mapping class group and Teichmuller space setting, pretty much anything that you could, like any notion that you could come up with of what you mean by like full measure, generic, or whatever, you end up with principal pseudo-analysis, or like principal foliations, i.e., so for the pseudo-analysis, it's that your invariant foliation has all three-prong singularities. So this also works in for foliation. So if you take the hitting measure on the boundary of Teichmuller space, you get that generically. This is also what's full measure. And so we kind of are like that.
What does it mean non-geometric R trees?
Okay, so an R tree can be dual to a, like singular measured foliation on a finite simplicial 2 complex. And as it's one way that R trees can show up that are quite complicated. In fact, it's how they're showing up in like a mapping class group setting. And so the non-geometric part, actually what we ended up showing is that typically you do not come from a foliation on a finite simplicial 2 complex. So that piece of it was a big piece on its own that kind of we were trying out for a while. We were additionally able to get that the branch points are all trivalent. There is a subtlety here in that we have an index sum that isn't fixed by the Euler characteristic. So we have like an index inequality, and that can determine the number of these, like, well, once you quotient by the out of R action, the number of these singularities, these like trivalent branch points. And we don't actually know how many is typical. And I think this is one of the complications that makes this uncertain what's going on. Okay. So here's to your question. So in most nice settings, you have that if you want to take, right, so now you're looking in the quotient of your space by the action, so that instead of having the geodesics, you end up with these closed curves. And then you want to count how they grow, how the number grows as you bound the length of the curves. So in our setting, what we do, I'll say that, and then it kind of makes, so we're looking at conjugacy classes. So we restrict this to looking at conjugacy classes of fully irreducible. We bound the stretch factor, which actually bounds the length, because when you're looking at your axes, the log of the stretch factor should give you like your translation distance along it. So when you take this quotient, so we bound that stretch factor, and then we see that the number of these curves, and we're only looking at the ones that come from fully irreducibles, and the conjugacy classes actually grows double exponentially. So I should say, I tend to be lured into questions that are of a measure theoretic, ergodic, dynamical systems nature. Well, I don't have definitely not as much of an expert as I would like to be on these things. And so like my understanding is this definitely messes up having the Patterson-Sullivan measure be your invariant measure that you're looking at. If there's a way to get around this, so my giving the disclosing about my my liking things that I don't have all the background to understand it as well as I want to yet, is that I'm very eager to talk with people if they know what to do in these settings. Okay. So what this result I say tells me is that there's way too many geodesics. So one thing I kind of think about is, can we just restrict down what we're looking at? Because this isn't even looking at all of the axes for the fully irreducibles. This is conjugacy classes of fully irreducibles. Okay. Okay, so we have a lot. So what's another thing? So I'm going to go to another thing that kind of has been informing how I've been thinking, but in order to explain that, I need to explain. So way back, Lee-Mosher and I proved a condition for knowing when you do only have a single axis. So one reason that that's interesting is in that setting, I know how to construct these train track automata, which I'll describe a little bit later, that encode all these geodesics for these fully irreducibles. So I understand that in that setting, but also the reason why it's good to know that there's this algorithmically checkable condition is for this has been in the back of my head for a while. So with the Algom-Kfir and Kapovich, we proved this result, which we actually use in our random walk results, which are, so you have this lone axis criteria, you have this additional criteria. So I'm going to call like the graphs or these ideal Whitehead graphs that like capture the singularity structures that have this, I'm calling these dominant. I have reasons for that. But what they basically satisfy is that if you have one of these geodesics coming from one of them, and then you have another geodesic that like stays close enough for long enough, either it has the same ideal Whitehead graph. So we can think of it as being the same strata, because in the Teichmuller space setting, you stratify these geodesics by the index list. We're trying to do a similar kind of thing with ideal Whitehead graphs. And this is this weird circumstance I'm still trying to understand. We have something weird that can go on, like you identify vertices as you go along. This like drops you down to a different strata where you only have some number of the components. I altogether don't really understand yet the circumstance where you identify vertices. It's something that shows up. I don't really understand it other than the fact that you glue the components of the ideal Whitehead graph. But the point is, these dominant ones, there's not just like one kind that does this. So in rank 3, it would be like this graph, and this graph. My feeling, and I could be very wrong about this, my feeling is that the dominant ones somehow, they're like playing some kind of dominant role and that everything else is kind of like below them somehow. I've been trying to kind of map out how the geodesics interact with each other. Anyway, that's my feeling and I could be wrong. Anyway, just as kind of a side note, I constructed in rank 3, the automata for the first 2. One of those was a summer research project with an undergraduate student. Here it is. We used it actually in some later work with some other co-authors, but that's just fun. So I don't actually kind of explain what I mean by these automata. Now I kind of have this idea, I think maybe these like trivalent things are kind of dominating the behavior. But maybe it's also all these dominant ones that have this fatal strata property, and then there's things below. Anyway, I've been playing with the automata to see if they can help me understand what's going on. So what do I mean by the automata? So remember I kind of like, I stratified these geodesics by their ideal Whitehead graph. Right now I'm just talking about ones that come from fully irreducible, but one could have a more like expanded version of what we mean by that. So I've like kind of clumped them by their singularity structures basically. And then what I've done with these singularity structures, so I'm going to take a graph that like carries the fully irreducible, and I'm going to put these singularity structures into the vertices. So what that ends up doing is now I get a graph where the lamination leaves run through this train track structure. Okay, so, right, because these encoded how the lamination leaves could run through. And then the fact that this is a different color, for those who can see, for those who can't, I made this a different color. The reason that that's a different color is because it somehow is, it's like, it doesn't show up asymptotically. It's not an asymptotic thing, but it is important in understanding how the lamination lives inside of the graphs. So these are the nodes. I'm going to form a directed graph. I have a notion of preserving the train track structure. And then the edge between, so I have an edge from this vertex to this vertex, right, which each look like these train track structures, if I can do some kind of fold that takes me from this one to this one, okay? I want to give the caveat that I still don't understand the identifying vertex situation, and so I did not do this in that setting. That's something to be done, maybe over winter break. We'll see. Okay, so I get these, right? So this is what they kind of end up looking like. You have these train track structures, and then you have these folds that preserve these train track structures. And then what ends up happening, so in this situation, basically where we're avoiding identifying vertices, if I have a loop in there, it gives me a train track map. It might even get, if I have additional conditions, it gives me a fully irreducible with that ideal Whitehead graph. And then again, in a nice enough setting, I know, so every fully singular train track representative of fully irreducible determines a loop in one of these. So it's like it's Stallings fold decomposition. It's the edges in there. The last thing is that any bi-infinite path in there determines a geodesic in outer space. So basically, once I've got this automata, it's telling me, so now I've kind of expanded a notion of having that ideal Whitehead graph, just not just from the fully irreducibles, but basically anything where I have one of these bi-infinite paths in there, and then I've encoded all these bi-infinite paths with that kind of singularity structure, and that would live inside of that particular automata. So kind of where am I going with this? So one thing is I was kind of talking about before, I had this idea that there's these ones and they fit inside of each other and so on. I have an idea how to do this. I haven't finished writing this up, of how the automata kind of nest inside of each other. So in the circumstance of where the vertices are identified, I am working out what's happening there. That one I have less of an idea than the first one. First one, I feel like I've basically worked out. The second one, I kind of have ideas of working out, but I'm not sure I'm going to make it work. So the third day, when I go up to Montreal, so Chichek and I, we're trying to work out, we have this cubist structure of the axis bundle with particular kind of like preferred, you know, splitting sequences or folding sequences, because right, we have this idea that there's like so many geodesics for each fully irreducible. So we end up with a finite number of these, and then we kind of use them to construct the structure of the entire axis bundle. So in hopes of, we're kind of trying to understand what the different representatives have to kind of narrow down what we're looking at. So here's my, perhaps naively, my belief is we don't have an ergodic geodesic flow. Why do I believe this? Because we have like these different dominant behaviors and so on. I might be wrong. I think we don't, but I want to understand what exactly we have.
What measure do you have?
Well, yeah, you have to figure out what measure makes any sense, right? Because you can't just do the Patterson-Sullivan measure or something.
I don't know. I'm asking, do you have a measure relative to which you?
So I don't. I feel like that's one of the things that we need to figure out. Is there any measure that we can make sense of what's going on? Sometimes I do, this is being projected and recorded. I won't name any names of people who they're like, oh, but I know how to tweak the measure, the Patterson-Sullivan measure. And then it's like, oh, wait, that doesn't work. But yeah, one does need a version of a measure that we can actually work with. And then, yeah, I want to understand what the flow looks like. I don't think it's going to be as nice as the Teichmuller flow or something. And so I have my reading also, and I do get reading homework from people as to what I should read to understand how different kinds of flows could look and so on. You're welcome to give me more reading homework, as in what is, if you have some, that would be great. But yeah, this is the thing that's eating in my brain. I timed it well, didn't I? So thank you.
Okay, any more?
Yeah.
Is your aim to let me put it differently. Can you infer from this some group theoretic properties of the outer automorphism group? I mean, so you have an algorithm to compute whether two things are conjugate?
Oh, well.
I'm just trying to, are you trying to understand the group theory? Are you trying to understand this outer space? Or are you just trying to understand the
So
story?
me personally, if I'm honest in life, I'm very driven by just the outer space picture. I do understand that better theorems would say more about the group also. If I'm going to be a completely honest human being, both of those things are are true in my mind. I just want to understand the picture just out of like not understanding the picture drives me a little crazy. And so I've kind of been picking at trying to understand it. It would be nice, and this is the thing, like in figuring out which geodesics are important, if we're just going to pick out some of them to actually understand, in picking out which geodesics are important, in finding the invariant measure, all these things, I believe these should be done within the back of our head that we're going to be able to show something about the group. And so that's where that comes in the back of my mind. I think we have to make some choices as to what we're actually doing. And for that, I think that for that, we should have some group theoretic thing in the back of our minds, I think. So if I'm going to continue to call myself a geometric group theorist.
There is some online question which asks whether, in this case, automata of a train track is is it a sort of approximation of the calligraph of the monoid of fully reducible axis process contains the train track?
I mean, so because remember that we have like the Stallingsfold decomposition is giving us the edges, right? So you have some number of folds or edges for each fully irreducible. So there could be, right? So there's, there's a relationship because it's only a finite number of folds, but we're also only looking at ones for like fully irreducibles and so on. There's also multiple train track representatives for a fully irreducible. So there's a relationship. It's not a very clean relationship as of yet.
Are there any more questions? Let's thank Catherine again.